Students, today we will learn about symmetric and antisymmetric wave functions. Suppose I have a wave function psi, which is a function of x. Then I can say two things about this wave function. One is, if x goes to minus x and psi also changes the sign, that is psi goes to minus psi, then such a wave function is called antisymmetric wave function. Antisymmetric wave function. That is, psi of minus x is equal to minus of psi of x. And the second case is that on changing x to minus x, psi does not change its sign, that is, it retains as plus psi. Such a wave function is called as symmetric wave function. Therefore, one can write that psi of minus x is the same thing as psi of x. So this wave function is called a symmetric wave function and this one is called an antisymmetric wave function. Now the question is, which type of particles classify for antisymmetric wave function and which classify for symmetric wave function? The particles called fermions, that is electrons, protons, neutrons, etc. I mean the particles which obey Fermi-Dirac statistics. Fermi-Dirac statistics. These have antisymmetric wave function, and the particle called bosons, which obey Bose-Einstein statistics. These include gas molecules, photons, etc. These particles have symmetric wave functions. In your previous semesters, you have already got to know in detail about Fermi-Dirac statistics and the particles obeying such type of statistics like electron, proton, neutron. They are spin-half particles, and these are full integer spin particles like photons, gas molecules, etc. Now, the next thing is that if this wave function psi was a function of more than one variables, we had chosen a one variable only, x. Now suppose it is a function of more than one variable, say 3, 1, 2, 3. I could have also chosen to write x, y, z, r, theta, phi, anything. Now I want to know how many solutions does a wave function in general have. We should remember that in general a wave function has n factorial solutions, where n is the number of variables on which it is dependent. Here it is dependent on 3 variables, so it has 3 factorial solutions, and we know that 3 factorial is 6. Let us classify those 6 solutions. These can be further classified under 2 headings, that is cyclic solutions and non-cyclic solutions. Now cyclic include these things. As an aid to memory, I'll draw a small diagram. You write 1, 2, 3 and then you go in a clockwise direction. So what combinations do you get? You get 1, 2, 3, 2, 3, 1 and 3, 1, 2. These are the cyclic solutions of this wave function. And what are the non-cyclic solutions? You go counterclockwise, that is 1, 3, 2, 3, 2, 1 and 2, 1, 3. These are the non-cyclic solutions of the wave function. Now, something more that differentiates a symmetric wave function from an antisymmetric wave function is in terms of this cyclic and non-cyclic solutions. For a symmetric wave function, one can write that it is the sum of all its solutions, cyclic and non-cyclic. That is psi of 1, 2, 3 plus psi of 2, 3, 1 plus psi of 3, 1, 2 plus this psi of 1, 3, 2 plus psi of 3, 2, 1 plus psi of 2, 1, 3. So a symmetric wave function is the sum of all its solutions, that is cyclic plus non-cyclic. While as an antisymmetric wave function is the sum of its cyclic solutions, 1, 2, 3 plus 2, 3, 1 plus minus the sum of all its non-cyclic solutions. So I'll not write it again, but it is cyclic minus non-cyclic in case of antisymmetric wave function and cyclic plus non-cyclic in case of symmetric wave function. This is one more property that differentiates a symmetric wave function from an antisymmetric wave function. And that's all for today.